Good morning. Today I welcome you guys to the 20th lecture of Systems Engineering, which we are going to discuss a specific functional analysis tool called Functional Flow Block Diagram. It's an important tool. So the Functional Flow Block Diagram is a tool that is used to conduct functional analysis, which is an important step. If you remember, again, as a quick recap of this, we had a loop. The systems engineering process loop had three things. The first loop is called as the requirement loop, or the requirement. Instead of the loop, we will call it as analysis. From here, we go to the next one, which is called as functional analysis. And then we have what we call as a design synthesis. So the requirement analysis gives rise to functional analysis. In this process, you go back and check your requirement analysis, and this is called as the requirement loop. Okay. Similarly, from functional analysis, once you have the output of the functional analysis, it becomes the input to the design synthesis, and you keep on iterating between back, which we call as the design loop. And you also have the loop with the requirement analysis, which we call as the verification loop. So, and then you have the systems engineering process basically manning all the three. You have seen that this model we have been discussing, we have been going through different aspects of it, different thought processes of it, and stuff like that. So one of the tools, and we have been discussing the functional analysis in the previous classes, and one of the tools that we mentioned there to conduct functional analysis in an efficient manner is functional flow block diagram. So what is a functional flow block diagram? So in simple terms, a functional flow block diagram typically defines task sequences and relationships. So the task sequence, this is the most important thing, and the relationship. So task sequence implies the order in which the tasks need to be completed or conducted. So the order, the specific order within which you complete the, or you sequence a task, that is one. And then also the relationship between the tasks, which task is related to who, that is also one thing. Okay. And another aspect also of the, this is typically also known as FFBD. This is the abbreviation of functional flow block diagram. Okay. And this is also it is usually called as, it's a traditional tool. It's a traditional tool whose origins are from the IDEF system. Okay. And also is that it also allows you to do, help you to identify, or in a way what you can say is that the simple rule that everybody follows in this, the simple rule within which the functional flow FFBD works on it is, you check and see whether all functions are verbs. Earlier we also mentioned that these are actions. Okay. So you should be using verbs to do this. Okay. If any are not verbs, okay, or any function is identified as a noun, then that means that there is a problem in understanding of the function, and hence revisit the requirements. It is almost impossible for any of us to really get the functions right at the first go. As I said earlier, it is again an iterative process. So the first thing that you do is in the functional flow block diagram is you check and see whether all functions, each and every functions are expressed as verbs. If any are not verbs, if any of the functions are not expressed as verbs, or you see nouns in the form of the verbs, then you know that there is a problem in understanding of the function. Okay, you basically find that okay, the understanding of the function is not clear to you, and then you have to go back to the requirements, or maybe you might have to conduct the requirement analysis at some point of time a little bit again to get clarity on that. A typical example of this is if I say somewhere, write it as a, as like somebody says, if I say perform surveillance, that is a verb actually. You are performing the surveillance. So you know what all things that need to perform the surveillance. Instead of that, if I write Sony digital camera, then this is a problem. This is not expected out of that. You are supposed to express what function you are going to do. To perform surveillance, it is not mandatory that you need to use a Sony camera. You can use many other cameras. You can use an infrared cameras. The aim is to identify what the functionality is, or what function we need to finish. That's the first thing, what the functionality is. Then, only then we check how to do it. Remember, I mentioned earlier also that that is part of the design synthesis. So we are not designing a system yet. No system design is going to happen at this point. We are just still working on the functional requirements. So the first part is the customer requirements. From there we got our requirements plus performance specs. That gets translated to what we call as functional requirements. And these performance specs should filter down to lower level functions. So the surveillance, perform surveillance this is a high level function usually. How would you do it? Okay, that is like gimbaled payload. Okay, you have a pan plus tilt mechanism. So there is many options. So first is you require a gimbal payload, from there a pan and tilt mechanism, then there is a zoom and focus mechanism. Then from there image analysis, analyze image. So you keep on filtering it down, and each time you move down from the perform surveillance, you might have a high level requirement of, like somebody says, identify a car at from 1000 meters. Then it boils down to how you get to do it to the lower level of functions. So the performance specs, which is usually attributed to the high level function, gets boiled down to the lower level function. That is primarily what the aspect of the functional analysis, and functional flow block diagram is a tool that actually facilitates the analysis of breaking down of the higher level functions into lower level functions, and as well as appropriately allocating the performance parameters that are associated with the higher level functions to the lower level functions. So, let us see the also let us see how does a FFBD looks like. The functional flow block diagram has actually three, I mean we can have multiple levels out of it also. Typically you find it in three levels, the first level here, then the second level here, and then the third level here. Okay. So, the first level is the basic functional requirement is what gets stated here. So, you state the requirement here. The basic functional requirements get stated there in the box. Okay. It could be something like perform mission or whatever it is, okay, for perform surveillance, conduct surveillance. So, this will be a verb format. So, conduct surveillance is a verb there. Okay. From there, you basically break this down into its component functions. There we just do as an example 2 component functions. There, remember, demonstrate the component functions. There can be any number of component functions. So, this is where this step, this process is also called as functional decomposition. So, you are decomposing the basic functional requirement into its component functions. The component function requirements are specified at this level. You are decomposing them into the component functions. Okay. Also, this is the time, this step also helps to aggregate functions. Okay. This sounds counterintuitive because you are decomposing. You are at this point you are decomposing the functions and you are also looking for aggregating them. First aim is to actually decompose them into component functions. The specific component, the constituting functions, what are to achieve the basic functional requirement. This basic functional requirement is identified, and from there the component functions are identified so that the basic functionality can be achieved. But then once it is done, you also look for opportunities to aggregate functions. Why do you need to look for opportunities to aggregate functions? Because this will help in minimizing what? It will help in minimizing interfaces. Remember, one of the aspects of aggregating functions is we can minimize interfaces. So, our aim is to ensure that the interfaces, the functional interfaces required as part of this is minimized. Then from there, once the component functions are identified, you go to the third level, decomposition of the component functions. So, the individual component functions are further decomposed into individual steps. What are the constituents? These are the constituting steps. You can always have a fourth level. I mean, this can further bring down, because if this component functions are further components, then you will have your further components in between and you will move this whole thing one level down. Here we assume that you can add other levels for further decomposition. But the last level is where you basically decompose it into the constituting steps of the function, and also at each constituting step you also do the specifications. The specifications associated with each step is also part of this process. I hope you guys have a basic idea of how the FFBD is designed, And again, as you can see, this is a tool that allows the systems engineer to exercise a lot more flexibility at the same time when he is doing the functional requirements. So let us do maybe try to do a simple example to see how this can be thought through. So I will actually take an example of the so again, before doing this, just as a recap, the functional architecture of a system this is the output of functional analysis is a top down decomposition of the functional and performance requirements of any system. So this is the first point everybody need to clearly remember. The functional architecture of a system, which is the output of the functional analysis, is a top-down decomposition of the functional and performance requirements of any system. So you are doing a top-down decomposition of functional and performance requirements of any system. Number two, the functional architecture will not just show those functions that are to be performed, but will also provide the logical sequencing or the logical sequence in which they have to be performed. This is important in a very complex system because it not just show what functions are to be done, but it also shows the logical sequence in which they have to be done. This is also an important aspect. Okay. Third one, the functional architecture also provides a description of tentative, we will call this as tentative or possible items to be used in the system. Okay. So this is a place where we provide a description of tentative or possible items. They are in inverted commas because in this process you are identifying alternatives. You are looking at whether it's a government provided item or a commercially off the shelf item or a specifically manufactured item. So, but these are like you are kind of giving clues to the designer that okay, we thought through this, we think these items would be able to do functional capabilities. Fourth one is the functional architecture should also ensure that performance requirements of high level functions is decomposed into lower level functions, but the important part is while maintaining sufficient flexibility for the designer. This is an important part. It is the duty of the functional analysis to break down the performance requirements of high level functions, the top level functions, into the lower level functions. You have to bring them appropriately down, but ensure, you have to make sure that maintain sufficient flexibility for the designer. If you make these performance requirements, it's in a simple way to say it is, okay, do not make performance requirements as into too much restrictive. So this is one of the things that you need, that the systems engineer need to ensure, that the performance requirements should not be too much restrictive, so that the designer finds it extremely hard to design the system or design the product. Okay, fine. So with these kind of 4 points that are critically important to the functional analysis, we would now try to get into the example, okay, of we'll try to take an example of the UAV, and then we will try to go from there. Okay, so in the UAV there is the one of the mission, let's talk about it, is the UAV should always communicate with the ground control station providing live video feeds and telemetry. Okay, this was one. And while maintaining mobility. This sounds like a tricky statement, because you are saying that the UAV should always communicate with the ground control station, providing live video feeds and telemetry while maintaining mobility. Well, the UAV is mobile, so whose mobility are we talking about? So the mobility in this case the user was talking about is, this question is like, whose mobility? The first question that we ended up asking is, whose mobility? Then the user clarified, is it UAV's mobility? If so, it is already mobile, or in a way it's flying, so there is no point in asking for its mobility. Then the user said, no, it is the mobility of the ground control station while UAV is flying. This was a tricky proposition for us. So think about this way. You have a runway here. You have your ground control station with the antenna right here. The ground control station computer and everything is connected here. The UAV takes off from here. Okay. It took off from here and it is flying someplace here. Okay. Assume that's flying someplace here. Okay. Flying around. Okay. It took off from here. This was the takeoff. Ideally, you would expect it will take off. It will fly up to some level where this is where its range. Okay. This is the range of the UAV. Okay. We will assume that it will fly until this range. Okay. Which is the range with the communication, because it should be in communication. This is the communication. This is what we call as the ground control, okay, the UAV. Okay. So then if that case, it should communicate back and forth between this send videos, and the UAV is mobile, this is ground control is fixed. Now one of the things that user wanted was, okay, once the UAV takes off, you can take this whole ground control and kind of move it here. So let's say now your ground control including the computer moved here. Now because let's say you have a runway here, then the UAV should be able to still maintain this communication, okay, communicate, and then come to this new area. So this was their way of enhancing the range. Now the range is kind of like this. Okay. So you might not have the capability to reach a target someplace here, or let's say instead of this range, we'll say the range is someplace here, and this was your, let's say, the target area. Said, okay, by doing this, we can get the UAV to come over here. This was their thought process, okay, and then observe the target. So that posed a new challenge to us. Okay, now we understand the functionality. The mobility is not a functionality of the UAV. The mobility is the functionality of a ground control station. So the ground control station which is typically stationary should be made mobile. The reason is the entire why? Because the GCS design, the ground control station is also called as GCS. GCS design is simple, can be fit onto a truck bed. So then we were like, okay, one of the major aspects of it is when the UAV takes off, we set this as the home. So if anything happens, if the communication loses, the UAV is supposed to come back here. But if we move the ground control station, then this will be the new home. It should come back here where the runway is. You typically try to move your ground control station. The rule is that GCS is usually close to the runway so that you can bring it back. So the home of the UAV, it can be dynamically, this need to be dynamically updated depending upon the location of the ground control station. When this aspect was put forward, we were like, okay, this is a new, completely new design challenge, a new system approach that the requirement that the user has put in, and we have to create a new functionality. Okay. So then for that, what you can think about is if you want to do a functional diagram, you can always say the first level, okay, you can say, think about as your first one, say perform dynamic home, you can say perform dynamic home as your first function, and let's say for the time being you can basically say that as your component functions as your second level, okay, where you can say is that it should communicate, should always remain in communication, right, throughout, and during this process sometime you will probably have transport home, or we will change it as transport GCS. This will also happen sometime. Okay. Usually, if when we discussed with the customer, they said that okay, once the UAV takes off, it reaches a this is, let's say we assume this as this cruising altitude. They would like to shift the home to this new location. So the aim is that okay, the UAV will continue to communicate throughout this process, but once it takes off, after some time into the takeoff and communicating, this is the point at which you can think about it as in the timeline. This is where the another tool called the timeline is important, because this is where the cruise altitude is reached. Okay. Then you transport the GCS, the UAV still remain in communication, and you set up at the new location, and the UAV continues to perform the mission. Okay. So then how much is the transportation? This we have to specify. So we said okay, the max it will do is something close to, we have said it as okay, it will move to somewhere close to 30 kilometers or 50 kilometers, and it would take somewhere close to 50 minutes to make this move, or 30 minutes to make this move, something like that. So we gave it 50 minutes as a time period and 30 kilometers as a time for it to distance for it to move. Okay. So then this one thing is this communicate function is one thing, but we can further see that this transport GCS can be further broken down. It can be broken down into the third level. Okay. And we can say that okay, it basically says once it is done, then we can say load, then you can say start, you can say move, stop, deploy. So the transport GCS would accomplish these steps, where you start load. Once the UAV has reached the altitude, then you load stuff onto the truck, and then okay, how much time for it to take this? We say 10 minutes, and the distance traveled is 0 kilometers. You're just loading, you're not done anything. Then start. So you start the truck and move. So we said okay, it takes 1 minute, and then again you are not moved any distance. And then move, we would basically say okay, it's about 50 minutes or 50 minutes or 45 minutes, and then you travel somewhere close to 30 kilometers. Okay. Then you stop, which is like again another 1 minute, and then 0 kilometers, and then you deploy, you will basically say another 10 minutes and 0 kilometers. So if you think about it, this actually provides you that okay, this total process is 10 plus 11, 11 plus 12, 12, 12 plus 10, 22 plus 45 will be about 67 minutes. We will be in this process. The ground control station will be mobile. So if you add to that, okay, fine, then we say, okay, this 50 minutes was a lower estimate. This is only for this aspect. So we need to make this as 67 minutes and something like that. So we keep on editing this, we revise it, to ensure that there is complete traceability, or we can find out how it was done. Okay. And this is where this kind of a thing is what we call as performance allocation. So if we say instead of 10 minutes, somebody says I want to make it only just 1 minute loading, then the problem is you are making it extremely, this will become an extremely restrictive performance requirement allocation. So providing sufficient time, okay, gives the time to the designer to design the system in such a way that he or she, the person who is utilizing the system, has sufficient time to do the job and get it done without anything. So this is also what we call as the logical sequence. Okay. And this is also another logical sequence, because you cannot do something like this. If you draw this diagram this way around, instead of this, if you draw this way, draw it like this, let's say transport GCS, and then you say communicate. It doesn't work because the reason is you first have to, the UAV has to do, the sequence is this: take off from location 1, reach cruise altitude, autopilot, sorry, that's the wrong way of writing it, engage autopilot. Okay. 4, transport GCS. 5, update new home. 6, update mission. Then 7, recover UAV. So if you go back to the previous diagram, the idea is that you take off from this place, you reach a cruising altitude, engage the autopilot. So this is where the autopilot gets engaged. So it ensures that the UAV will stay in this area, that particular area that you designated. Then you pack and move your GCS right here. Okay. The UAV will still remain in communication with the GCS, but the GCS is moving. Excuse me. Once you reach here, you engage the ground control system, and then this is where you update the new home, update home. So now the UAV knows that, okay, I don't have to go back here, I have to come here only to land. And then you tell UAV, okay, now this is your target. So up to this point, this is where your communication problem was. But because of this, now you are able to move your GCS, you are able to get to this target. So this is another aspect that was, this is the way it is to be done. So you can say that the communication comes before the movement of the GCS. So that logic, if you write it this way, then it becomes wrong. Instead, this is where the right way to write it. Okay. So this kind of a technique, what we just mentioned about how the functional flow block diagram can be used to break down a higher level function into a lower level function and a lower level function into its components, is an important thing, because you will have for every function, you will have one functional FFBD, function flow block diagram, and by going through this documentation you will be able to identify, okay, fine, what all things what we need to do to achieve this kind of a function, and ensuring that this traceability happen. You said, okay, fine, this 50 minutes is wrong, it should be 67 minutes, and you update that. Then it's totally fine that because this all the documents is in sync, and then you use this document to further study what is going on, and somebody says how this move happens, so what type of, somewhere you can say here that, okay, what type of it, somebody says, okay, we would choose a tractor truck or something like this. Then the idea is that, okay, then this whole base, we are, or we can say Tratra or some other 1, 2, 3, we would say these are the 3 trucks options that we think will do this trick as the mobile GCS. Then it allows the designer to choose an appropriate one from this, and then design, or maybe make a new choice completely altogether by himself or herself. Okay. I think giving this whole thing around, again the main summary point is that we have not discussed what we call as this timeline analysis, which we will do sometime later down the road once we finish QFD. But this timeline, somewhere here you can see that this timeline is there, and here also there is a timeline running in this process. Okay. So the time taken to perform this activity is an important aspect of this whole system, and this is what we actually end up doing as part of the functional flow block diagram. So just to recap what we did today, the functional flow block diagram, it defines task, sequences and relationships that we already seen, and we also said define time sequence of tasks. These two we have seen how it actually being taken care of today, and we will also see the tool called QFD, quality function deployment, that we mentioned briefly yesterday. We will also see that tool, and as well as we will also see the tool of timeline analysis, and then we will move into what we call as the design synthesis, okay, where we will talk about requirement allocation sheet and other tools. So thank you for your patient listening, and see you in the next class. Thank you.